Hello everyone and welcome to a new episode of All Things IDA. In today's episode we're going to be talking about Appcall. Appcall is perhaps one of those features that not many people are aware of just because it doesn't have an explicit UI element to it. So if you dig in the menus, you might not necessarily spot or even know that it exists. But let me tell you, if you've never heard of it before, hopefully in this video you will see how powerful that feature is, and hopefully you can start using it in your day-to-day reverse engineering workflow. All right, so let's get started. So as usual, we start with the SDK just to tell you where is Appcall and so on. So Appcall is in idd.hpp, is defined in a function called Appcall. And that's basically the root function that scripting either Python IDC uses behind the scenes. And this feature works disregarding which debugger we're using. Essentially, as long as we have a debugging session, an active debugging session, we should be able to do appcalls. So what are appcalls? Let's start with a simple example. Here I have a basic database I created, just a sample. We'll look at the source code as well in a second. But for now, to be able to use appcall, we have to start debugging. So here we are, we're debugging, we're suspended. Now, since we're gonna be calling functions within the context of the process, and those functions are in the process, we have to make sure that if we want to pick a function to call it via appcall, the environment is ready for that function to be called. So as you notice here, I put my breakpoint in main as opposed to start. So if I put my breakpoint at start, I might be able to call some functions if I'm suspended directly at start, but maybe they won't work because they require the C runtime to be initialized. So this is an important thing. We have to be in the proper context before we call that appcall function that we pick. So for this example, since I'm suspended in main, this is a console application and we don't have anything yet. We're in main. What I'm going to do is locate the function printf and show it to you. So here we have printf, as you can see, it's properly prototyped. And that's an important thing. We have to have a prototype to begin with. And we'll see why the prototype is important. So we do have the prototype. This is a good first step. And to issue the app call, the basic thing is we are in IDC. Let's switch to IDC here in the CLI and just directly call the function as if it was an IDC function. So the function here in the database is called underscore printf, takes a string and variable number of arguments. So here I'm gonna directly call it, just typing printf and say, for example, hello %s and word as the actual value for the format specifier %s. And let's put semicolon to make this as a statement and issue it. And just like that, I called printf and we'll have the side effects of printf. So as if the application called printf. And so if we look at the console window now, here we have hello world called. With this in mind, if I create a new snippet here, so for now here, if I switch to IDC, for example, auto I, and say for I equals 0, I less than 10, for example. And here you'll notice that we will be able to use printf nicely, for example, as well within a loop, within the script, and so on. So here, let's say like that, and run it. So just because printf exists, IDC will pick it up from the database. So printf does not exist in the IDC language, underscore printf at least. So let's run. And here as well, we see this is the side effect. Okay, so we've seen how to issue a simple call for printf, for example. And we've noticed printf is inside my actual database. But we can also call other functions that are not originally in the database, things that get loaded when we start debugging. So debug modules, essentially. So let's see the modules list here. Here in the modules list, I have just kernel, basically, an NTDLL and the exe. Now suppose we want to inject a DLL. Let's say we want to load user 32. That's another venue where we can use the app call. So first, let's see where is load library. Load library is inside kernel 32. So we go to that location. And here we are. Now we cannot directly issue the app call I could if it had a prototype. So if I say load library A down here, but what do I pass? How would I then know what to actually, how to formulate the app call and so on and so on? We'll talk about mechanics, how app call works behind the scenes. But this is not enough. So really, one big prerequisite for app calls is to have a proper prototype. One way for standard names is to rename the function to its standard name. So we get rid of the current 32 underscore prefix and just rename it to load library. Once we do that, IDA automatically knows what's the prototype. How does it know? It knows from the loaded type information. In the type library, it has this information. Now that we have the prototype, let's include this in the names list. And now all we have to do is simply issue the call by name. So here I'm going to switch to rename it, get rid of the prefix. Also, it doesn't have to be called like this anymore. The reason I call it load library A is just to have the prototype for free instead of me typing it. I can call it load lib if I wish. Now, at any point here, I do have a load lib. In fact, in IDC, if I type a symbol name that has a label, it will resort to an address. So whenever I load lib like this, I got its address. Anyway, what we want is an app call. So we just say load lib and we pass the proper arguments. Here I'm going to call load lib user32 and enter. The moment I did that, we see the side effect of calling load library in the context of the process in the currently selected thread. So right now, if we open the threads list, I'm in the main thread and the load library happened in the context of the main thread. If we want to issue a function call, an app call, and another thread context, all we have to do is just simply double click to switch the thread. And then now the app calls, future app calls will be in the context of the selected thread. So let's switch back to the main thread. And we can re-inspect the modules list. And we see indeed that user32 has been called. One last demo I'm going to show you along that topic. So now with that we have user32, let's say we want to call message box. So same story. Message box now became available after we did the load library. Let's give it a prototype by removing the prefix and bring it back to a standard name. And now we can issue the app call. So let's do that. So now we're ready to actually call the message box. Same story, if I want, I could have renamed it to MSG box and call it. So MSG box requires the handle, the parent window handle. I don't have a window handle that's suitable for now, so I'm gonna pass 0. Text, this is an app call. This is an app call, for example. It's a regular IDC expression, so I'm adding strings and so on. And then the caption, let's say this is a caption, and the type. So type one of those MB underscore constants. And we don't want to really hard code those stuff. So these are the U type. It's not a good idea to hard code them. And when we use app call, even this is even outside app call, it's part of IDA. In fact, if we can directly call the MB OK and have it resolve in IDA, as long as that type IDA knows about it. So let's go to the enums window, insert, and add the MB underscore constant. So I bring in one and I get all of them, at least the ones that IDA managed to group together. And now I have MB OK, MB cancel, MB yes no, and so on. So if I want, for example, if I open the calculator, any enum symbol you can type and it will resolve. This is part of the IDC language and its integration with the IDA kernel. So here if I say, let's say MB default mask, I get the value. So for my actual API call, here I can actually, now that I imported the enum, I can say MB OK. And how nice is that? Like I don't have to hard code anything, keep it clean and so on. So issue that message box, enter. And here we have, since I didn't specify a parent, it came through the desktop as the owner. And here we are. The application is blocking. The app call did not return, so IDA is blocking. So be mindful of that as well, that the app call will block the whole of IDA. Once we accept that, the app call will finish, IDA will take back control, and everything will work as expected. So here we go. I got the message box, I got even the result of the message box, and we're back to IDA. Now let's talk about a bit more complex cases. So here in this is the source code of the program that we're looking at. We're dealing with structure called user records. It has some fields and so on. We have some helper method like make record, for example. We give it a name and an ID. It returns a record. Let's see how we can deal with that Appcall and retrieve a native pointer to a memory allocated record. But initiate that in IDC and continue, issue the Appcall, get that record and use it in our script. So we do have make record. Let's double check the prototype. It looks correct. It returns this. And let's open the local types, make sure that the type exists. So I did also add, just copy pasted the proper structure needed. And now it's available in the type information. So IDA knows how to deal with this. So let's make a record. First, I'm going to create a global variable just for to keep track of it. So extern R. And now let's say R equal make record. And let's say alias 123 and enter. I did create a record. It's in R. Now, if I want, I can inspect R. R has the side effect of actually allocated memory on the heap and so on. So let's see what we're dealing with. If I type R, IDC will simply dump that object. So inside that object, this is what we have. We have add. This is a special attribute that designates where is the actual underlying native object. Then we have the actual serialized brought in as a higher level access to us. So this is the actual programmatic way we can use name and ID. So here in IDC, since I have R as an object, I say R.ID, I got the value, and I say R.name, I got the value. It's a zero terminated string, and it has some junk because the make record did not clear out the whole buffer. And we can verify that by simply going to the underlying native object on the heap. And if we actually apply a record, user record, we should be able to see the, let's go to the struct window and just make this decimal and make this as a string. And this is a pointer. Let's double check. It is a correct pointer. Okay. So here we have the same representation, really, the ID, the name, zero terminated, and all those stuff coming from malloc and so on. So this is very nice, basically, how we can do all of this natively. Now we have another helper method in that database called print record. So let's as well, now that we have an IDC object called R, which is proper record backed by real object, we can pass the R variable that we have to print record. So let's do that. So here as well, so far we don't have anything. Let's say print record R and see what happens. And we're calling a native function. So print record, it got called, and this is the output from the actual application, the way it handles that record that we allocated. Now let's take it one more step and try to, if you notice here that user record is a singly linked list, so we can actually chain records, and we're gonna do that as well. We're gonna create a couple records and link them together and see how IDA intelligently knows how to deserialize such relatively complex structures. So this is not necessarily super complex, but it can be, as long as we have the types. IDA will go infinitely and serialize those types nicely and make them available to use through scripting. So let's do it. What we did earlier through the CLI, I replicated here. I have the records, a variable make records, and we display the attributes that we got from make record as we discussed. These are coming from the actual object in memory. We are using print. Print is IDC's way to dump an object. We don't have to show it for this case. So let's just make one record. I don't need to print for now. Let's make another record. Let's just give them serial IDs and one more record. So let's make 3 records and link them up. So now that we have those records, remember a record has next field. So that's what we're gonna do. We're gonna link them, 1 links to 2, links to 3, and so on. So rec1 dot next equal rec2, and rec2 dot next equals rec3. And then we're gonna issue a list record, the function. It takes the head and just goes calls print record one by one, advances to the next. So that's the one we want. So list records. So now let's issue an app called list records, and we give it the head. So since R1 will lead to R3 based on the way we link them together, this should basically print all the records. Let's try it out. And this is the output. Records 1, 2, 3. Of course, if we linked it differently, so let's link them differently and reissue that. Here, let's print just some separator. Print F here, and now we have like a small separator, and it doesn't matter how we link it. So if I link rec1 to rec3 and rec3 to rec2, it will now display them 1, 3, 2. So here we have 1, 3, 2. And that's another advanced use case of how we are naturally interfacing with the underlying debugged process using high-level language. Now, these are concepts I'm explaining in IDC, but they're very similar in IDA Python. But let's say we want to call get command line. We can do that as well by simply resolving the address and then applying a type permanently. So we don't have to go by hand each time. Remember when we are going to, let's say, message box, and I had to edit the prototype and so on. Even if I put the prototype once, I stop debugging. If this is a debug segment, the prototype will be gone. So if our script needs to be, or our code wants to run over and over again, we have to make sure that the prototype exists. And maybe we can make that part of our initialization of the script. And that's what we're doing here. This part here just initializes the proper environment. So resolve the get command line, and then uses apply type at this address and gives it a prototype. That will apply it for that debug session. And now we can simply invoke get command line because IDA now knows how to actually interpret that function call. So let's run it. And this is the actual command line that was passed. We can verify that. So it is the application plus the parameters. And that's how we did it simply. This initialization step we have to do only one time. Subsequent times, given that variable, all we have to do is just call it. So for example, let me show you this trick. So let's go to get command line, and you'll notice it does have a prototype. So we have a prototype. Now, if I want to call it each time, let's say, I can say location by name, this one. This will return an integer, which is also callable. We can just say, since it doesn't take any arguments, I'm passing nothing, and this have the same effect. So similarly, if I went to message box and did the same, like first, since I didn't apply the prototype, but let's now give it back the original name, for example. And we can say a location by name, which returns a number, which then we can use that number as a function pointer and then issue the call. So here, title, caption, and MB, okay, MB, yes, no. Let's see. And here I got the app call by simply casting this becomes like a function pointer, and then this is the actual arguments to the function. Yes, no, let's say yes, and I put semicolon here, so let's not put semicolon so we get to see the answer. So here the answer of yes is 6, and here is 7. ID, yeah, I think ID yes, ID no, something like that. I'm gonna show you one more example here. that is calling something a bit more advanced. Let's say find first. So we're gonna call find first file even, something a bit more complicated. And that will give me a chance to explain a bit how we can work with such stuff. Now that's the find first file API. Find first file takes an input, file name, and an output, Win32 find data. This is the actual result of the call to find first. The find data is a structure. Look how complicated it is. So it has substructures, a file time substructure, file name, alternate file name, creation time, etc. So this can be complicated if IDA does not give us the convenience, but we can have that convenience very, very easily. So let's try to break that down easily. Since this function requires first a basic type, so we can pass this as a regular IDC string, but how do we pass a structure, a Win32 find data? And this one is an output argument. So because it's an output argument, this is even better. IDA is smart enough to accommodate a generic object to make it of the form that the Appcall requires. So let me explain. So here we're using the low-level function debug Appcall, which this is the low-level function. Instead of typing a function name, we can also use this low-level function that takes the destination we want to Appcall, that also takes the prototype, and then after it takes a prototype, we can start passing the actual arguments to the Appcall function. So whenever we use the dbg_appcall, we have to pass two initial arguments, the address and the type. Now, if we don't want to pass the type because we know the type exists, we can pass 0. 0 means IDA should guess the type based on the address. So it will go check the prototype at the address, and if it exists, that's enough. But we know that since we're referring to debug symbols, every time we run, we're losing the prototype. So here is a nice way as well to directly issue an Appcall while also passing the prototype. So those two first arguments are needed for Appcall, the prototype and the address. And now these are the two arguments being passed to find file. This is what we want to find, and this is the Win32 find data structure. So how are we getting this? This is how we're getting it. We are assigning to a variable a generic object. This object will, IDA, before calling the function, will query the actual position of that argument. Say, so you passed me a skeleton object, an empty object, but I know it should be of the form Win32 find data. So it goes, allocates enough memory, and initializes an empty find data since we did not populate it. So if I had fd.object and I needed in-out arguments, I would have, say, fd.whatever field that I want to initialize, say, I don't know, C file name equals something. If that was needed as an input, that will be also serialized and passed to the actual underlying API. And it returns a handle. So here we're doing the Appcall, we're passing the find data object. And then if we got an invalid handle value or -1, we say we didn't find any files. Otherwise, we are displaying the field called C file name. And then what I'm doing is also doing another Appcall. The first two arguments are important for Appcall, and I'm telling we are going to give you the handle that we retrieved from find first. And then I'm giving you back an FD as well. Please populate it with the find next. And now this will enumerate. And then I'm calling find close, same story. The first two arguments are important, location and prototype. And then the argument. Let's run it. And here I enumerated using find file API all of those exes because that's the actual logic. Find exe files and so on. So I'm gonna stop here for this video. Let me recap real quick. So we introduced Appcall, the concepts, how it works in IDC. We call basic methods. We showed also how to call complicated API calls that require nested structure. We also showed you how we can call other APIs or functions in the database that have a semblance of linked lists or pointers to other structures, and that is handled naturally by IDA. I hope you found this video useful. For the next video, we're gonna continue. We're gonna cover how Appcall works and how to use it as well inside IDA Python. Thank you, and see you next time.